Assalamu alaikum, dear students. Welcome to the lecture of the classical mechanics. In this lecture, we will discuss the solution for the problem number 7.26. The statement of the problem says that determine the Hamiltonian and Hamilton equation of motion for a simple pendulum. The first part A, and then B part is simple Edward machine. Mean we have to find the Hamiltonian and Hamilton equation of motion for two systems, the first simple pendulum and the second Edward machines. No, look, let's go to solution. The first is simple pendulum. This in this case we have a bob which is attached with some mass and with rigid support like this, and this string has length L, and this is displaced from its mean position at an angle theta, so it will oscillate as simple harmonic motion. So Lagrangian for this system will be equal to T minus U. The first is kinetic energy. So kinetic energy will be equal to M over 2 and V square. So V will be equal to, you know that V will be equal to L and theta dot. V will be equal to L and theta dot. So V square will be equal to L square theta dot square, and then plug this V square into this equation, so this will give us kinetic energy. And then potential energy, you know that when we resolve this length into two component, this will be L sine theta, and the second, this will be L cos theta. So potential energy will be equal to mgh, because this is in negative y direction, so this will be equal to minus mgy. So Lagrangian will be equal to T minus U, kinetic energy and potential energy. So y is equal to minus L cos theta. Okay, then plugging this y into this equation, so this will become ml square theta dot square over 2, and this minus sign will become positive because of this minus sign, so it will become mgl cos of theta. Well, now we have found the Lagrangian of the system, and we can find the canonical momentum, which is equal to P theta is equal to partial L over partial theta dot. When we differentiate this Lagrangian with respect to theta dot, this will give us the canonical momentum, which is equal to ml square theta dot. Plugging this Lagrangian into this equation will yield this canonical momentum. And then Hamilton equation of motion. Now we have to find the Hamilton equation of motion from this Lagrangian and generalized momentum. You know that we can rearrange this generalized momentum and find theta dot from this expression. This will be equal to P theta over ml square, and then we have Hamilton equation, which is, since u is velocity dependent and the coordinate transformation are time dependent, the Hamilton is thus the total energy. So we can find the Hamilton H is equal to P theta dot minus Lagrangian. We have P theta and theta dot and Lagrangian. When we plug the above value into this equation, this will give H is equal to P theta square over 2ml square minus mgl cos theta, which is equal to total energy. It means the energy of this system is conserved. And also we can see that u is velocity independent, mean total energy is potential energy not depending upon the velocity. And coordinate transformation also, it does not depend upon the coordinate transformation, are time independent. It means total energy will not change with respect to time, and the system is conservative. Then equation of motion is theta dot is equal to partial h over partial p theta, and the second p theta dot is equal to minus partial h over partial theta. We have h, just plug this h into this equation and differentiate with respect to p theta. This will give us p theta over ml square, which is theta dot, and the second is p theta dot, which is equal to minus partial h over partial theta. Plug this h again into this equation and differentiate now with respect to theta. This will give us minus mg L sine theta. These are the equation of motion for a simple pendulum. Now let's go to part B, which is for simple Atwood machine. In simple Atwood machine, we have two masses attached with the help of pulley, and the mass of one is m1, which is at distance x1 from the pulley, and the second has mass m2, which is at distance L minus x. Because the total length is L, when we subtract this x from length, so this will give L minus x. Because the total length is this whole length is L. When we subtract this x with total L, so this will left with L minus x. So kinetic energy, first we will write the kinetic energy, because we are going to write the Lagrangian of this system. Then from that we will be able to find the Hamiltonian and Hamilton equation. So kinetic energy is equal to m1 over 2 x1 dot square plus m2 over 2 x2 dot square plus kinetic energy of this pulley. So pulley has rotational kinetic energy, and you know that, which is equal to I over 2 omega square, which is nothing but x dot square over a square. So omega square is equal to x dot square over a square, because you know that V is equal to R omega, and V is x dot, and R is the radius of this pulley, which is equal to A. So x dot over A is equal to omega. So omega square will be equal to x dot square over A square, and plugging into this equation 1 by 2 I is the moment inertia, omega is x dot over A. So its rotational kinetic energy will be equal to I over 2 x dot square over A square, plus this is translational kinetic energy. So our total kinetic energy for this system will be equal to kinetic energy of these two masses plus kinetic rotational energy of this pulley, I over 2 x dot square over A square. Okay, and then potential energy. Potential energy for this block will be mgn m1 g into this distance plus potential energy of this system. So you know that potential energy is equal to mg minus mg x, and for the second potential energy will be equal to m2g height. So height is, you know that height is equal to L minus x for the second. And why this minus sign is placed? Because below the reference we have negative y direction, and above the reference we have plus y direction. So we have placed negative sign with potential energy for the first block, and similarly for the second block. Okay, now we have obtained the kinetic energy and potential energy, and we can find the Lagrangian of the system. So Lagrangian of the system will be equal to T minus U. We have kinetic energy and potential energy. Plugging this kinetic and potential energy into this expression, this will give Lagrangian, and from this Lagrangian we can find the canonical momentum Px, which is equal to partial L over partial x dot, and which will be equal to m1 plus m2 I over a square and 2 x dot. Okay, at this position we can find the value of this x dot, and further this will lead to x dot is equal to px over m1 plus m2 plus I over a square, where I is the moment of inertia as already discussed. When we plug this equation into this equation, px and x dot minus L, we have a Lagrangian in the as previously, and px and x dot. You know that is when we plug this x dot into this equation, so this will give us h is equal to px square over 2 into m1 plus m2 and this, and minus Lagrangian this whole. Okay, so we have obtained the Hamilton for this equation. Then equation of motion, you know that x dot is equal to partial h over partial px. We have h, just plug this equation at this parameter at this point and differentiate with respect to px. This will give us this, and similarly px dot is equal to minus partial h over partial px. Again take this h and plug at this equation and differentiate with respect to px, so it will yield to m1g minus m2g, which can be written as g into m1 minus m2. This is the equation of motion for the x coordinate, and similarly for px dot coordinate. Okay, so I will stop at this point and discuss the next question in the next lecture.